Welcome back to Water Quality in the Pacific Northwest. Today we're going to start a new unit. We're going to talk about the oceans. We're going to talk about water quality in the oceans and pollution within the oceans. We are going to have 5 lectures talking about the ocean. Components of these units include, we're going to talk about acidification of oceans. We're going to talk about coral reefs. We're going to talk about mangroves. We're going to talk about plastics, waste, and pollution. So our first lecture today is to talk about we're going to talk about the acidity of our organisms in the ocean. The organisms in the ocean evolved under waters with high pH conditions. As you would suspect, if you change the pH of water, the organisms living there are going to have a hard time adapting. And this is one of the concerns we have with ocean acidification. Scientists have measured that our pH values in our oceans are slowly dropping. And we call this acidification. As pH drops, we take on acid tendencies. Now, ocean acidification can be viewed as a negative change in ocean water quality. So this is a pretty big topic. It's going to get bigger and bigger over time. We are seeing right now, or scientists are observing, that with acidification, as pHs are dropping, marine life is not as vibrant as it once was. And this has alarmed many people. The cause of this acidification in oceans is pretty simple. So let's take a look at the cause. The drop in pH currently being observed in oceans is due to human-caused carbon dioxide additions to the atmosphere. In a matter of just a few years, we have seen the decline of communities, plant and animal communities in the ocean. Here's a pretty striking picture. This is in the Florida Keys, and we're looking at the difference in plant vegetation, 1976 on top, 2016 on the bottom. Now, these changes in the vegetation could be due to many things, but an overlying factor is the pH of the oceans has declined a little bit, and a lot of people think this is really what's changing the vegetation in the oceans. So let's take a look a little bit at the cause of ocean acidification. The drop in pH is currently observed in the oceans due to human-caused carbon dioxide additions to the atmosphere. Now, you've heard that story before. These human-caused carbon dioxide additions to the atmosphere have been linked to climate change, and now the science is pretty good that it's also linked to ocean acidification. So we're talking about burning fossil fuels, putting carbon dioxide into the atmosphere. We know, or 99% of the scientists firmly believe, that that is causing climate change. In most cases, we're talking about global warming. But remember, the Earth's surface is over 78% the ocean. So some of that carbon dioxide is getting into the ocean and is creating what we call ocean acidification. So if we take a look at humans and carbon dioxide emissions, we know that human carbon dioxide emissions, due to the burning of fossil fuels, have climbed substantially since the Industrial Revolution. And we know that these carbon dioxide emissions have climbed because of burning primarily fossil fuels, oil, coal, and natural gas. Now, there are other sources of carbon dioxide in the atmosphere, but the fossil fuels dwarf this carbon. The vast majority of this carbon dioxide output into the atmosphere is due to these 3 fossil fuels. In addition, the burning of recently produced biomass is also responsible for carbon dioxide emissions, although at a much lower level. Burning firewood puts carbon in the atmosphere. Burning trash puts carbon in the atmosphere. Basically, burning any organic material, such as maybe peat for fuel, puts carbon dioxide in the atmosphere. But collectively, firewood, trash, organic materials is a small portion of the carbon dioxide that humans are putting into the atmosphere. Okay, so we know what acidification is. It's the change in pH or the lowering of pH. So let's look at the science behind the pH change in the oceans. So if we take a look at ocean water pH, traditionally ocean waters have been slightly alkaline. pH values have been higher than 7. Now, if we take a look at the pH data that we have, scientists are seeing a shift of pH values on a downward basis as the pHs are dropping toward neutrality or dropping toward pH 7. The research data out there indicates that over time, ocean pH values will continue to drop and edge towards slight acidity. Scientists have measured pH in our oceans over time, and they do measure this shift. If we take a look at surface pH values, we've noticed that there are some bands across the ocean where the pH has dipped quite a bit. In the North Atlantic, in the South Pacific, Atlantic, Indian Ocean. But there are currents in the oceans, and the the water moves around. So overall, you're seeing a slight decrease in pH. Now we know that we've been told for the last 20 years that carbon dioxide emissions in the atmosphere are causing climate change. But we haven't thought about what's happening to the oceans. It's estimated that 30 to 40% of the human-caused carbon dioxide emissions are absorbed by ocean waters. So let's take a look at the chemistry of this. The basic reaction is carbon dioxide goes up in the atmosphere. Some of it falls to the surface of the ocean. When carbon dioxide comes in contact with water, we get carbonic acid produced. That's very important. The carbonic acid molecules dissociate into bicarbonate and hydrogen. Hydrogen ions are acidity. Remember, pH is the negative log of the hydrogen ion concentration of a substance. So the more carbonic acid we get in the ocean, the more dissociation into bicarbonate and hydrogen we get, the acidity, and that's what lowers the pH of the water. So because of this, the carbon dioxide is coming from the atmosphere, and humans are putting the carbon dioxide in the atmosphere. Because of this, we know that acidification is human-caused. This process is linked to climate change, and oftentimes people call ocean acidification the evil twin of global warming. Today, you're getting scientists saying that ocean acidification is as serious a problem as climate change. Again, let's take a look at the chemistry of acidification. We take carbon dioxide from the atmosphere, which humans put up there. It comes down, hits the surface of the ocean water. It reacts with water, and you get H2CO3 or carbonic acid. The carbonic acid dissociates into bicarbonate and hydrogen ions. And remember, hydrogen is acidity. Eventually, we get the carbonic acid and the hydrogen's acidity. And this is what's important, the hydrogen ions. The more hydrogen we have, the lower the ocean pH will be. Okay, so why is this so important? We take a look at a few diagrams here. We basically, here in this diagram, you see atmospheric carbon dioxide hitting the surface of the ocean. It dissolves, the carbon dioxide dissolves in the presence of water. We get carbonic acid. And you get bicarbonate ions formed, but eventually what you're getting over here is the hydrogen ions, and this is our problem. Another similar diagram, atmospheric carbon dioxide turns into dissolved carbon dioxide, reacting with water. You get this carbonic acid and acidity. The more hydrogen you have, the lower the pH of the ocean will become. Now, on a numerical basis, if we take a look at the historical data that exists, we know that between 1751 and 1996, the ocean pH has dropped from about 8.5 in 1751 to 8.14 by 1996. Well, a lot of you would look at that and say, that's a drop of 0.11 pH units. That's not much drop at all. Aha! But you have to remember that pH is expressed as a logarithmic scale, and that means the hydrogen ion concentration has actually increased in the ocean by 30%. So basically, dropping from a pH of 8.25 to 8.14 is a 30% increase in acidity in the oceans. So even though the pH change has been very little yet, just changing 1/10 of a pH unit has increased the acidity of the ocean by 30%. Now, if we take a look at carbon dioxide emissions and see that they continue to increase, ocean water pH is projected to drop another 0.3 to 0.5 units by the year 2100, 80 years from now, as the oceans absorb more carbon dioxide. The exact magnitude of this pH change will depend on mitigation and emission pathways taken by human society, such as if we reduce the amount of carbon emissions over the next few years, the pH drop will not be as severe. So if we put these numbers together and we take a look at projections, we can create a table here. Okay, in the left column we have the year. Second column we have the ocean pH. Third column we look at the pH change compared to pre-industrial times. And then we look at the hydrogen ion concentration change. So let's just look at the pH values. Pre-industrial, 1760s, ocean pH was about 8.2. In 1990, ocean pH is about 8.1. Right now, it's 8.069. Projected in 2050, about 7.949. In 2100, projected about 7.8. So if we take a look at this pH change, these pH change numbers seem very tiny. Up to 1990, compared to pre-industrial times, the pH had only changed 0.07 units. In present, pH has changed 0.11 units compared to 1750. Projection for 2050, pH values in the ocean will have dropped 0.23 units. And in the year 2100, pH will have dropped 0.355 units. Now remember, because pH is expressed on a logarithmic scale, a small change in pH really represents a huge change in the acidity. So the concentration of acidity in the oceans has increased 19% between pre-industrial and 1990. present here in 2019, excuse me, acidity has increased 29% in our oceans. The projection in 2050 is, compared to pre-industrial times, the acidity concentration in our oceans will have increased 70%. And by the year 2100, based on projections, the acidity of our oceans will have increased 126%. It's this last column where we have the fantastic numbers, and this is why we're very worried about them. Now, if we just simply plot pH over time, we can see the trends. There is a marked trend. If we look at the year and we look at ocean pH, you can see there's almost a straight line of pH dropping in our oceans. Okay, so now it's established that pH has fallen. pH is projected to fall even more, so that acidity will increase. I guess the bottom line is, so what? What does dropping from pH 8.2 to 7.8 actually mean? So that's what I'd like to talk about for a few moments. Based on the previous graph, the acidity of the ocean will more than double in 40 years. Well, this may be too great of a change for many of our marine species to adopt. This could have a big impact on humans because food chains and food webs are very complicated in the oceans. We don't understand them very well. You start disrupting food webs and food chains, and remember, humans get a significant portion of their protein from the oceans. That could have a major impact on human welfare. So basically, why does this acidification matter? Many marine organisms get their structure by removing calcium carbonate from ocean water. Organisms want calcium carbonate. For organisms to get this calcium carbonate from water, there has to be an excess of carbonate in the water for the organisms to obtain this calcium carbonate. You start acidifying the water, and the excess of carbonate diminishes. If there isn't excess carbonate in the water, some of these marine organisms have no way of obtaining this calcium carbonate, and thus they collapse. So acidification, the big problem with acidification is it reduces free calcium carbonate in the water. The process of an organism removing calcium from the water is called calcification. If organisms can't calcify, they can't survive, and many of the food web structures in the oceans may be doomed. That's the problem. So let's look at calcification for a few moments. The process of calcification is important to the biology and survival of a wide range of marine species. If they can't obtain calcium carbonate from saturated ocean water, they do not survive. Basically, what microbes in the water do is they precipitate calcium carbonate from the dissolved ions in the water into structures, shells, corals. It's all precipitated calcium carbonate from the saturated calcium carbonate in the water. pH goes down, you don't have saturated calcium carbonate in the water, so the building blocks that many organisms need are not going to be there. So all of a sudden, the structures are vulnerable to dissolution. These things have been built with calcium for billions of years. Because there isn't an excess supply of calcium in the water, not only can they not be built, they're subject to dissolution. So without saturated concentrations of carbonate ions, these structures may deteriorate. So acidification reduces carbonate concentrations which organisms need. Excuse me. Again, carbonic acid basically steals the carbonate needed by some marine organisms for their shells. You add carbonic acid to the water, which is, a product after the carbon dioxide reacts with water. The carbonate is what the organisms want, but you take the carbonic acid and react it with carbonate, you end up with a compound that the organisms do not need. A pretty famous researcher came up with what's called the Bergeron plot. And basically, this graph shows the change in carbonate, saturated carbonate in seawater, with acidification of the ocean. So here we have present, this blue line going through here, and we can take a look at the carbonate concentration, or the CO2 concentration in the water. And as we drop the pH, we see the CO3 of the carbonate concentration go down, which means the water is not saturated anymore, and then the saturated carbonate that the organisms need is less available, and they either starve or they are not as productive. So this line right here, this black line, is very key. So what this graph is saying, you can refer to it, it shows the change in carbonate within seawater systems from ocean acidification. Basically, the plot predicts that organisms that depend on calcium carbonate for their survival are in trouble with further ocean acidification. So that graph shows you how carbonate ions are important building blocks in the ocean. Lots and lots of species have evolved to use these carbonate ions, and they need to be in a saturated condition for these organisms to be able to get them out of the water, precipitate them, and they need to be in saturated conditions so that these carbonate ions, or this carbonate which is precipitated, doesn't dissolve back into the water. So let's look at some of the impacts, potential impacts. A resulting decrease in pH will have negative consequences for calcifying organisms. Organisms that form coral reefs will now have to contend with acidification in addition to warming temperatures. And we'll talk about warming temperatures in the next unit for coral reefs. But we've always assumed that the problem with coral reefs is that temperatures are too warm. Well, all of a sudden, if the oceans become a little bit more acidified, these coral reefs are calcium carbonate structures. They're not going to be able to build these structures very readily if there isn't excess saturated calcium in the water. There's a lot of different organisms, categories of organisms that are negatively impacted if you don't have this saturated calcium in the ocean. A lot of these organisms could disappear, or their importance in the ocean will be much less. And if we just quickly look at some of these organisms, some of them we know a little bit about, a lot of them we don't know much about. The coccolithophores, they precipitate calcium. Here's an example of one of these organisms. Calcium structure, very important for them. Another one are corals. We all know what corals are. We've heard about coral reefs. We know that coral reefs are very beautiful. But all of this is calcium carbonate. Let's look at a coral reef. You start losing the saturation of the carbonate in the water, and these organisms can't build these reefs. They can't build these solid structures. So all of a sudden, our corals and our coral reefs may be in jeopardy. We have other classes of organisms that we don't know about every day, as they're not everyday terms. The foraminifera, They look a little bit like these, but these are full of calcium. They're very important in food chains in the ocean. You start losing them, and what's going to happen to our food webs? Another group are the echinoderms. A term that we don't know very much about, but if we pull an example of an echinoderm, all of a sudden we know what they are. Starfish is an example of one of these. It pulls its calcium out of the water. Without that excess calcium in the water, these organisms won't exist. We get a little bit closer to the human food chain. We look at the crustaceans. The crustaceans, again, get their calcium from the saturation of the seawater, and all of a sudden crustaceans will be in trouble. Another category of organisms that would be very hurt by ocean acidification are mollusks. Again, an example of a mollusk. Again, these may be history if the ocean's acidified too much. In addition to these categories, something that's very, very important for food chains are our zooplankton in the water. These are little organisms, are very small, they're tiny drifting animals, and these animals are eaten by bigger animals to move up the food chain. These zooplankton are very, very important. They build their shells made of calcium carbonate. So they need that extra, that saturated calcium in the water. And you don't have the zooplankton, you've got the key player in marine food chains in trouble. So these plankton are big players in food webs of the ocean. So another potential problem with ocean acidification. So the two major types of zooplankton, the tiny drifting shells, they make their shells of calcium carbonate, are very important. So what I've tried to do is I've tried to give you some background for why ocean acidification is such a big issue. Basically, we're worried about changes in food webs and food chains in the ocean. If saturated calcium concentrations decrease, with decreasing pH of the ocean water, the oceans are indeed in trouble, or they're indeed going to have some serious changes. Remember, it's someplace between 10 and 20% of the protein humans consume is marine-based. One thing we haven't talked about at all is fish. Simply, acidification may deprive fish species of their most common food. And remember, the fish species eat, smaller fish, which eat the zooplankton. So we start getting rid of the zooplankton. If they become less healthy, there's less food out there, so there's less organisms. In addition to lack of food for fish, you have to remember that marine organisms evolved to adapt to pH conditions of about 8.2. You drop the pH, and all of a sudden that puts stress on an organism. Can their cytoplasmic pH adapt to a lower ocean pH? We don't know about this. There is evidence on land that they can't, or at least in freshwater. Excuse me. At least in freshwater lakes, they can't. We talked about lake acidification in the northeastern part of the United States. Well, basically, fish species have gone out of those lakes because the pH of those lakes has fallen so far that the cytoplasmic pH of the native fishes has not been able to adapt. So in summary, ocean acidification is a big deal. It's a component of water quality in oceans, and it's an issue that humans have to deal with. And if we can deal with climate change by reducing our carbon dioxide emissions, that will also help the plight of our oceans as far as pH. Thank you for your attention. I'll see you in the next lecture. This is a topic that's getting bigger every year. There are a lot of people out there that think ocean acidity is as big a problem as climate change because the acidity of our oceans is very much related to climate change. So let's start off by talking about